Okay, so let's go on with section chapter 11.3, solubility. So even most highly water-soluble compounds have a limit to how much you can dissolve. We've seen this with salt and with sugar. You can eventually get to where no more will dissolve. And when we see that, that's typically we'll see some of the solid laying in the bottom of the container. So solubility is the maximum concentration of a solute that can be achieved in a particular solvent under given conditions, and that's always temperature dependent. So it depends on what temperature you have. So when the solute's concentration is equal to its solubility, the solution is called saturated, and we will see some solid in the bottom of the container. When the solute's concentration is less than the solubility, we will not see any solid. It could be saturated, but it could be unsaturated, so you would have no way of telling without consulting a chart. And when the solute's concentration is greater than its solubility, the solution is called supersaturated. And that solution is very unstable. The smallest change will cause the solid to crystallize out. So, to the extent to which a solute dissolves in a solvent depends on several factors. One of them is the nature of the solute and the solvent. What kind of interactions do they have? The temperature at which you're doing this dissolution. And when dealing with a gas solute, the pressure is also important. We're mainly going to be concerned with solids dissolving in liquids, but we will talk about the gas situation first. So here we have a solubility chart for, 5 gases, and you'll note that each one of those, as temperature increases, solubility decreases. And that's because both the solvent molecules and the solute molecules have more energy as temperature increases, and so more of the molecules of the gas have enough energy to escape the surface. This is what happens when you pour soda into your cup and you see a lot of foam coming out. The carbon dioxide solubility is low enough that it will come out of the solution. So you should keep your soda cold before you pour it so that more of the carbon dioxide remains dissolved in the soda. So, pressure has a major effect on the solubility of a gas of a liquid, and I just kind of talked about this. Solubility of a gas would equal the concentration, gas solubility, and the partial pressure of the gas. K is a constant, and that would be particular to the liquid gas system that we're talking about and the temperature. We are not going to calculate any pressure gas solubilities. But an increase in the partial pressure leads to an increase in the solubility of a gas. And that's the idea behind those things that you can put on your soda where you press and you pump more air or more into the solution or into the 2-liter container to help the solubility of carbon dioxide remain high so your soda doesn't go flat. Henry's Law and carbonated soda I'm not going to talk about, but I am going to talk about liquids can be dissolved in other liquids. We are going to talk about both the solute and the solvent are liquids, and what does that mean? So examples of that would be I could mix 2 liquids together and they have to be miscible. This is another one of your vocab words. That means that they mix together or they form only one layer. An example of something that's miscible would be ethanol and water. We can dissolve those two in each other. We can dissolve oil into gasoline, but I cannot dissolve oil into water. And when you look at salad dressing like vinegar and oil salad dressing, that's an example of 2 liquids that are immiscible or not able to dissolve in each other. So if we look at this as an example of water and oil, oil is the top layer because its density is lower than that of water, and so it is the top layer. And these are a nonpolar liquid with water. So Sometimes things are partially miscible, which means they have a low solubility, but they will dissolve somewhat. And when I take on the left, I have a test tube of liquid bromine. In the middle, I have a test tube of water. And on the right is where those two have been mixed together. And we can see that it forms two layers, but there is some of the orange color dissolved into the water layer. And so we know that a small amount of bromine did dissolve into the water. So that would be partially miscible. When we have something like sodium bicarbonate, we can, this is sodium acetate. Sodium acetate has a fairly high solubility in water, and it will form sodium ions and acetate ions. And typically, when we have a solid dissolving into a liquid, it could be endothermic or exothermic. And so it is usually endothermic, but we can have formation of products which may give back some energy. And we talked about this at the very beginning of this. We have to break the interactions between the sodium ions and the acetate ions. We have to break the interactions between water molecules, and then we get some energy back from making interactions between water and sodium ions and water and acetate ions. So the solubility of most solids tends to increase with temperature, meaning that if I heat something up, I can get more to dissolve in it. And that's true with things like sugar, that's true with sodium chloride, all sorts of ionic compounds. If I want to make a supersaturated solution, and I think I'll try and demo this for you, we have to start with a solid solute. We make a saturated solution of the compound at a fairly high temperature, and then we have to slowly cool it without disturbing it, and it'll remain all in solution until I do something just as easy as tap the glass on the outside of the container, or I could drop in an extra crystal or a grain of sand, and it would all start to precipitate out. And so as we lower the temperature and the solid remains in solution, then we have a supersaturated solution. There's a YouTube if you want to go there and see it. So I'm going to stop here, and we'll talk about colligative properties later. See you later.